Hey everyone, Adam the Tutor here, coming at you with the second part of our video series on, well, Fourier Series. And this time we're talking about the orthogonality of sines and cosines. So, first of all, what do I really mean by that? Well, basically when we talk about orthogonality, we think of, if we have, the vectors, u dot v, that their dot product is equal to 0, right? This means that u and v are orthogonal. And in fact, u and v could form an orthogonal basis for, another vector, let's say w, right? U and v could form an orthogonal basis for another vector, say w, right? If we had, something like, alpha times v plus beta times u, right? So this will be perfectly fine. So assuming, of course, u and v met the other criteria for a basis. But, okay, well, that's basically what we mean when we say two vectors are orthogonal. And more generally, we would have that two vectors, now we're using vector in a more mathematical sense, right? If we had, the function f and g, if we had the following condition, if the inner product of f and g was equal to 0, then we could say f and g are orthogonal, right? And at this point, if you haven't had any exposure to, the more advanced topics in linear algebra, I'd recommend, you brush up on that. I will be making a video series on linear algebra as well. But if you know what I'm talking about here, then equation 1 right up here makes sense, right? Because, well, what's the inner product of a function? Well, the inner product of a function on a given interval is f times g, and usually if it's a complex vector space, then you'll have to have this dual. But right now we're just dealing with real functions, so it's not really that applicable. So basically, this guy is this guy. This is just a more abstract notation for inner product. So, and again, both in this case, our f of g our f and g that I'm alluding to are, of course, cosine and sine, right? And these are real functions, so we don't have to worry about the complex conjugation. But basically, what I'm getting at here is I'm alluding to what I said in the previous video, where I said that cosine and sine formed a valid basis for a series representation of f of x, right? And that's what equation 1 is saying, right? Equation 1 says sine and cosine are orthogonal on, we'll say, minus a to a, right? Which is what we want, right? Remember, we care about the orthogonality on an interval because we're representing f of x on an interval, right? So that's good. So now that we've kind of gotten that out the way, right? What are these other two equations, right? We have equation 2, and let me go ahead and switch to red here. We have equation 2 and equation 3. What are these guys saying? Well, basically, we're using equations 2 and 3 to find our alpha sub n and our beta sub n, right? Because essentially what we're doing, and I'll do the example with alpha sub n, and it's the exact same process for beta sub n, but with a sine instead of a cosine. What we're doing is we're taking equation 6, right? Equation 6, and we're multiplying through by cosine of pi m over a of x, right? So cosine of pi m over a times x, right? That would be equal to, well, we'd have a naught over 2 cosine m, then over a x, and we'd have plus. Now at this point, we're assuming that this series right here converges. So I can integrate it. I can take the integral sign within the series. So we're not worried about that. So I'd have, because we are going to be integrating, right? Min equals 1 to infinity. Then we're going to have alpha sub n. We're going to have cosine pi nx over a. Oh, and then I need to multiply that by cosine pi m over ax plus beta n sine, I'm just going to call it k sub n, just to save me some writing. And then this will be cosine k sub mx, right? So basically what I'm saying is here, I'm saying that kn is equal to pi n over a, and km is equal to pi m over a, right? Just to save me some writing. Okay, so now what we want to do is we want to integrate this, right? So we integrate from minus a to a, so there's a dx. We integrate from minus a to a, there's a dx. We integrate from minus a to a, dx. Integrate from minus a to a, and then of course dx. Alright, so, well, we know this guy right here is going to be 0, right? Because basically, we're integrating over symmetric interval. We'll have a sine. There'll be an a over pi m, which comes out, and we'll have a sine here, and we'll basically get sine of pi m, minus sine pi m, or plus sine pi m. And so basically this will cancel out and be 0. Now, what about this one, right? Well, that's why we have equation 2, right? This is just equation 2, which says that basically this becomes a delta sub n m of a, right? And what does this mean? Well, basically this equals 0 when n doesn't equal to m, and it equals 1 when n is equal to m, right? That's what this symbol right here means. So if n is not equal to m, then this is 0, but if n is equal to m, then this is equal to a, right? Now, what about this one? Well, this is just equation 1, right? So this is also 0. So now, what we have is we have that this integral right here, f of x cosine, and I'm just going to write this, is going to be equal to, now we have this, right? Summation from n equals 1 to infinity, alpha n, and we're going to have delta nm times a, right? Because that's what this integral right here equal to, right? And this guy is 0, right? Well, again, remember, what does this do? This says that n has to equal m, otherwise it's 0. So then this is just alpha m times a, right? Because when n is equal to m, this guy is just 1, right? And now we can solve for a sub m, right? So then we have a sub m is equal to 1 over a, right? Just dividing that, times the integral of this guy. Right? And of course, if you want, you can rename m to m. It doesn't really matter. Just as long as you do it to both sides. But this right here, lo and behold, is actually equation 4. Right? So this is equation 4. Right up here. Right? And that's how you solve for these constants, right? And you can go through the exact same process using equation 3 and using equations 1, 2, and 3, and doing the same process, but instead of multiplying both sides by cosine of k sub mx, you do it with sine of k sub m times x, and you'll get equation 5, right? I'll leave that to you to do, just because, hey, don't really feel like doing it again. And it's a good exercise to do on your own to really kind of get a feel for what's going on here. So that, I think, just about does it for orthogonality of sines and cosines. And also a note when doing these integrals right here, you're going to need to use the exponential formulas for cosine and sine. So you have cosine of knx is equal to e to the ix plus e to the times k sub n, and then there's an I here, and over 2, and then sine is this is a 2i and there's a minus sign here. Right, so you're going to need to use those two and then multiply out, and then you're going to need to evaluate the two cases when n doesn't equal to m, and then when n is equal to m. Of course, when n is equal to m, this becomes squared, and then you can just use half angle formulas to evaluate it, and it's really not too bad. But basically, that's really all there is to this. And that's really the meat and potatoes behind Fourier Series. Just the previous video and then the topic covered in this video. That's really the meat and potato of Fourier Series. And I think that's going to do it for this video. If you have any questions or any comments or anything like that, just drop them in the comment section below. I will do my best to address those. And as always, thanks for watching, and I will see you in the next video.